Hello everyone, and by now you must have understood the content which I have given about the Compton scattering, and you must have gone through all the derivations. If you have any questions related to the derivations to get this Compton effect or Compton wavelength, please feel free to ask on the WhatsApp group, and the derivation I have given you as an home assignment, so please go through it, and if you have any confusion please ask. You have to also go through this example 2.4 which is important to understand, and which is also very easy and explained. So this example 2.4 you also include in your home assignment. So leaving this Compton scattering, and we have covered the photoelectric effect and the Compton scattering, which gives you the flavor about the electromagnetic radiation as the particle nature of the photon. Now today we will try to understand the de Broglie wave. Okay, so how to start to understand what actually the physical significance of de Broglie wave. So you can see that the de Broglie in 1924, when he proposed that moving objects have wave as well as the particle characteristics. So de Broglie in 1924 proposed that the moving objects have a wave as well as particle characteristics. So if you recall your earlier understanding that the electromagnetic wave behaves as a particle for the photoelectric effect and the Compton scattering, and there's another phenomena that's like diffraction interference, in which you have the electromagnetic wave is behaving like a wave. But this for photoelectric and the Compton scattering establishes that the electromagnetic radiation is behaving like a particle, and this particle is the photon, the quantization of the electromagnetic radiation, which consists that if electromagnetic radiations consists of a photon, the smallest energy quanta. So basically, let us discuss first the dual nature of the electromagnetic radiation, or the wave particle duality. And to understand this, let us come to this water ripple. You can see that these are the two sources of the water ripples. Means one slit is here, one slit is here, and then the water is coming from this side and from this side, and then when it passes through these two slits, and the ripple interfere with each other, and we see the spectrum here. We see the spectrum, bright and the dark spot. And you know that there are certain positions where the constructive interference is there, somewhere destructive interference, and I have, like here, there is no destructive interference, so no black and white spot is making here, so we have a black dot. Here we have spot, blacks, dark, white, dark. So we have a pattern of interference. So the diffraction is taking place, and then interference is taking place, and then due to interference and diffraction we have a spectrum here. So this made us think that because the water ripple is a wave in which the amplitude of the height of the wave is changing, and it gives me a pattern. If the two waves when interfere with each other after diffraction, that gives me a pattern. So this is a pattern spectrum which is due to the wave nature of something, wave nature of the water. So what this is, this was the idea when so we have seen that the water waves gives me a spectrum like this. So if we think about the electromagnetic radiation, so if we do the double slit experiment with the electromagnetic radiations, like here we have a monochromatic planar wave, that is a laser beam is coming towards a two slit, and then we have a spectrum like this on the optical screen. So the waves, the electromagnetic radiations interfere, diffract at these two slits, and they interfere to give exactly the same pattern as we are getting in case of the water ripples. So we know that the water ripples is a wave. So if this electromagnetic radiation is giving the same spectrum as the water wave is giving, so naturally one considers that the electromagnetic radiation is behaving like a wave when we do the double slit experiment in such case. Now suppose we do the same experiment with the particle. Okay, if we consider the particle, if you consider a sand particle, if I have two openings and we have a screen here, if we blow the sand particles and consider is a sand particle, if you blow the sand particle from this direction, then what we expect is that the two position of the sand accumulation. So one is this and one is because of this slit, one is because of this slits. So we're not getting the same pattern as just because as we get in case of the waves are coming at these two positions. These are the sand particles. So what we expect, the screen with two slits, and on the optical screen we get two distinct lines where the sands are getting accumulated. So this is the particle nature we expect. Now let's see what will happen when we do this experiment, double slit experiment, when we consider the electrons, because we consider electrons as a particle. Okay, so the first case I'm going to discuss is the multiple electrons. It's a single slit experiment. So if I have a single slit and if I project electrons on the slits, naturally I'm going to get the depositions of the electron on the screen like this. But when we do a double slit experiment, so this is entirely displaying the particle nature of the electron, this experiment. But when we have a two slit experiment, and when we project electrons on these two slits, then what I'm getting is a pattern, the same pattern which we get in case of the wave behavior. So if you have single slit experiment, this is exactly showing the particle nature of the electron, because we are considering electron as a particle, and it is. But in the double slit experiment, we're getting a same pattern as in case of the electrons are behaving as a wave. Okay. So when multiple subatomic particles were projected on double slit, they behave in the wave pattern, and when multiple subatomic particles such as electron when projected on a single slit, they behave as a particle. So let's consider as the third case where the electrons shot one at a time. So what is the difference between this and this is that here a beam of electrons are coming all together, but now in this experiment we have a control over the electron. So I'm sending electron one by one towards the double slit experiment. Okay, so electron shot one at a time. So again we are getting a pattern, a view on the screen, which is like when these electrons are behaving as a wave. Okay, so on the other side, this is the same experiment, but what we are doing, we are placing a recorder. The electron shot at one time, but at this slit we are putting a recorder, and this slit we are putting a recorder. We try to see which electron is coming from this slit, which electron is coming from this slit. So in that case, what we get is exactly the particle nature. So electron shot at one time showed particle nature which observer detect. So the two complete behavior. When I am tagging the electron, then the electron is behaving as a particle. When I'm not tagging the electron, and electrons are free to go from any slit, he has to decide whether he has to go from this slit or this slit. He is behaving like a wave. This is a very weird observer effect. So electron is behaving like a particle as well as a wave, just in the two cases of the experiment. So electron changes from wave nature to particle nature when being recorded. It is really strange that conscious observer is affecting the experiment, especially with recorder near the electron. So the final conclusion which we can make from here, that the water wave spectrum is exactly the same when we do the same experiment with the electron, which is behaving as a wave in one case and as a particle in another case. And the same way, so we can say that the electron, which is established particle, it in two different conditions is behaving as a wave nature, and it is showing its particle character in the two different scenarios. So it's a wave particle duality for the matter. And the same we have seen that when we do these kind of experiment with the electromagnetic radiation, not with the electron, then electromagnetic radiation behaves as a particle in case of the photoelectric effect, in case of the Compton scattering, but it also behaves as a wave character when we do the diffraction experiment, when we do the interference experiment. So there is a duality in the nature of the matter. So why I'm saying matter? Because the matter behaves as a particle as well as a wave, and all these experiments gives the de Broglie his hypothesis that a moving matter can behave as a particle as well as a wave. So now let's come to the de Broglie wave. So what de Broglie thought that the nature always choose the symmetry. Nature always choose the symmetry. He thought that when electromagnetic radiation is behaving as a wave as well as a particle, why not every matter? So he proposed that a moving body, that is a matter, behaves in a certain ways as though it has a wave nature. So he started with the photon, because we know exactly about the electromagnetic radiations. The photon or light of frequency nu has the momentum p. We already know. We can write it h nu by c, and this h nu by c, because c is equal to nu lambda to h by lambda. So the wavelength of the photon is then specified by the momentum. Okay, so if a particle has a momentum is related with the particle, and the wavelength is related with the wave. So the photon is therefore specified by its momentum according to the relation h by rho, because p is equal to h by lambda, and lambda is h by p. So de Broglie suggested that this equation is completely a general equation. We can apply this lambda h by p, a general equation, to any material particle, as well as the photon which is a particle with no mass. So when we do material, that means we are considering the mass. So this de Broglie suggests that this equation is completely general one that applies to the material particles. So he just modified it. The momentum of the particle of mass m and velocity v is p equal to gamma mv. Gamma is basically gamma is 1 by under root 1 minus v square by c square for the particle which are moving in with relativistic velocity. So the de Broglie wavelength is written as lambda is equal to h upon p equal to gamma mv. Okay, so what he suggested that the greater the particle momentum, because he has written that lambda equal to h upon gamma m and v, and gamma is 1 upon 1 minus v square by c square. Fine. So the greater the particle momentum, the shorter its wavelength, because this is h upon p. Okay. So as in the case of electromagnetic wave, the wave and particle aspects of the moving bodies can never be observed at the same time. So what he's saying that at the same time when the matter is moving or the object is moving, the matter can show its particle nature or the wave nature, only one at the same time. So we therefore cannot ask which is the correct description. All that we can say that it is a certain situation, a moving body resembles a wave, and in other it resembles a particle. So depending upon the situation, we can decide that what kind of nature this matter is showing at this moment, whether it is acting as a particle or behaving as a wave. And which set of properties is the most conspicuous depends upon how its de Broglie wavelength compares with its dimension and the dimension of whatever it is interacts with. So what is the rule of finding that whether it is behaving as a particle or it is behaving as a wave? So that we have to know that if the de Broglie wavelength of that matter particle, we compare its de Broglie wavelength with the dimension of the matter and the dimension of whatever it interacts with, this comparison will give us the idea that whether this matter is behaving as a particle or behaving as a wave. Okay, so to understand this, let's come to this example, which is asking about find the de Broglie wavelength of a 46 gram golf ball which is moving with a velocity of 30 meters per second, and an electron with a velocity of 10 to the power 7 meters per second. So the first is when a 46 gram golf ball with a velocity of 30 meters per second. So because 30 meters per second is much less than the velocity of the light, so we can safely set gamma equal to 1, because the gamma is 1 upon 1 minus v square by c square. So v is less than c, so this is almost 0, so this gamma becomes 1. So we can take gamma 1, so lambda is h upon mv, because lambda is h upon gamma mv, so gamma is 1, so we can write gamma lambda is h upon mv, putting the value of h and the mass of the golf ball and its velocity. What we are getting is the wavelength of the golf ball which is moving with 30 meters per second. Now you can see the wavelength. The wavelength of the golf ball is so small, 10 to the minus 34, compared with the dimension of the ball, the ball, that we would not expect to find any wave aspects in a behavior. So if the wavelength, de Broglie wavelength of a matter is very small as compared to the size of the matter, then naturally we are going to have the particle aspect and not the wave aspect. On the other side, if we consider the electron which is moving with 10 to the power 7 meters per second, in fact 10 to the power 7 meters per second is also less than the velocity of c, which is approximately 10 to the power 8 meters per second. So if we can also take gamma here 1, gamma in this case 1, we can take gamma 1. So m is 9.1 × 10 to the minus 31 kilogram of the electron. So if I calculate lambda, so it comes out to be 7.3 × 10 to the power minus 11 meter. But suppose that this 10 to the power, the hydrogen in the hydrogen atom, for instance 5.3 × 10 to the power 11 meter is the radius of the hydrogen atom, and the electron, this is the nucleus and the electron is here. So the wavelength associated with this electron is 10 to the minus 11 meter. So the de Broglie wavelength associated with the electron is incomparable with the radius of the system in which this electron is revolving. So this is almost comparable. So we can, it is therefore not surprising that the wave characteristic of the moving electron, it is key to understanding the atomic structure of the behavior. So in this case, where the de Broglie wavelength is comparable to the size of the system in which we are dealing with or interacting with, therefore the wave characteristic is important to understand that behavior, that interacting system or that matter particle. So now you know that when a matter is going to behave as a particle or behave as a wave. Okay, so there is uncertainty. So from there, if you remember, we have uncertainty principle in quantum mechanics. So this is what the de Broglie wavelengths suggest, that every moving particle or matter, in fact, can behave as a wave and as a particle, and it depends on the situation in which it is interacting, that whether it is showing its particle nature or its wave nature. You can also go through example 3.2, which says to find the kinetic energy of the proton whose de Broglie wavelength is 1 Fermi. That is 1 Fermi is 10 to the minus 15 meter, which is roughly the proton diameter. So for the kinetic energy, you can use the formula that the kinetic energy is the total energy minus its rest mass energy. E naught basically, E naught you can write here, E naught is the rest mass energy, which is m naught c square. So this is 0.938 GeV. So the kilogram is converted into the electron volt, you'll get 0.938 GeV. So when we deal with the subatomic particle, we have to check whether the particle which we are dealing with is moving with the relativistic velocity, or we can treat as a relativistic particle or the classical particle. To do so, we have to compare in this formula that with the PC, this PC is greater than E naught, or PC is less than E naught. So when PC is greater than E naught, this is relativistic and this is classical treatment. Relativistic treatment is important in this case and the classical treatment important in this case. For example, in this case, for this electron, if you calculate PC, because P we know gamma mc and gamma mb hg by lambda, if you put all these things, so we get 1.24 GeV, which is PC is this, which is greater than its rest mass energy 0.938 GeV. So PC is greater than rest mass energy, so we have to use the relativistic calculation. The total energy is the rest mass energy plus b square c square. I can put all this in this expression and then we can find the corresponding kinetic energy with E minus E naught, rest mass energy subtracted from its total energy. So this is what we get. So you can also go through this experiment. Now the proposal of the de Broglie has also been confirmed experimentally through electron diffraction experiment. So it's not that it's only hypothesis, it's already confirmed. Now what is wave, or especially the matter wave we are talking about? What are matter waves? So like a wave, you think about the material wave, which is like a longitudinal wave or the transverse wave. It's not the longitudinal wave or the transverse wave. It's not a material wave. The Broglie wave is not a material wave. It's not electromagnetic radiation in which the electric and magnetic field are changing. Okay? It's not a sound wave in which the pressure is changing. So what it is? Because in all these waves there is a certainty. But when we talk about the matter wave, there is uncertainty about its behavior as a particle or as a wave. So the quantity whose variation make up matter wave is called the wave function, which you already know from a little bit understanding of the quantum mechanics, and which is represented as the psi. Okay? So, and we can only say about it's the probability psi mod square, which is psi star psi. So the matter wave is the quantum mechanical wave function, a wave which is always associated with the matter when it is moving. Matter when it is moving. As you can see that this wave is nothing but a kind of a group wave, like if I make a wave group, so this is like make a kind of wave group. So this is the matter wave. Somewhere the particle is there. So when this particle is moving, a matter wave is associated always with which is governing its motion. And this is our psi. And if we calculate its psi square, it gives the probability of this matter where it is located, whether it is at this position, where it is this position, where it is this position. So there's an uncertainty in its location and momentum. So our second thing, if the momentum is very high, if you suppose the momentum is very high because P is h by lambda, so lambda is h by P. So if the momentum is very high, so wavelength will be very small. So that means the wavelength is very small. So we are not going to observe the wave character if the object of the matter is moving with very high momentum. So naturally it is going to behave as a particle, not as a wave. So matter wave is not your material wave like longitudinal or transverse wave, not electromagnetic wave in which the electric and magnetic fields are behaving, or light wave I can say. So it's just the quantum mechanical wave function, the quantity in which what is varying is the wave function. The wave function is varying. It's like a wave group. It's like a wave group. So, and the probability of the particle or the matter is given by the probability density of the wave function. So the uncertainty, we will take up the uncertainty part of the matter wave in the later class. So you can say that, how to show this. You see that it's a classical picture of an electron in motion, and this is the matter wave picture of an electron particle in motion. Always a group wave is associated with this particle. Okay, so we thus find that in order to describe the properties of matter as well as those of light, we must imply waves and corpuscles, that means a tiny particle, simultaneously. We can no longer imagine the electron as being just a minute particle of electricity. We must associate a wave with it. So, and for this hypothesis, G. Broglie got its Nobel Prize in 1929. And in fact, many of the wave particle duality, this hypothesis gives in chemistry, SPDF structure of this. So these are all shaded portions are giving you the probability of electron being is more here and more here, more at this position, more in this position, not at this position, these positions. So these are the wave function, probability density wave function. The particle in this is more here, these are more here, not at these positions. So particles, when I'm saying particles, these are the probability of electron being present in this position in S shell or P shell or D shell. So electron is a particle, but inside the atom it is behaving as a wave, and this wave has a certain uncertainty, and that uncertainty gives you the probabilistic nature of finding that electron in its corresponding shells.